Okay, well, we'll get going here this morning. This is the second, well, it's actually the third, but the first one got canceled in our webinar on energy efficiency in agriculture. This morning we're going to talk about energy efficiency in lighting. This program is supported by grant from SARE. We have a regional grant for professional development. We've got some funds from DOE through the State Energy Office here in Wisconsin, as well as the University of Wisconsin and the University of Wisconsin Extension. So this morning we're going to talk about energy efficiency in agriculture. Let me just get something set up here, and lighting. Need my pointer so I can mark stuff. There we go. So we're going to cover kind of what's going on with some energy bills. We're going to start off with a 101 on lighting. Lighting is electromagnetic radiation, much like the way a cell phone or a TV or radio waves or X-rays work. But this happens to be in a light spectrum that, or wavelength spectrum, that the human eye can pick up and detect. And it goes from 360 or 380 nanometers to 760. Although within that range, humans can pick up more in the middle of that wavelength range than out on the edges. And just a perception of how our eyes work. And different animals can see different wavelengths. You know, there's some animals that only see black and white, etc. So those are the wavelengths. Now, what is light? Basically, it's illumination that's within that spectrum that we can see, and the way it's measured is, well, foot candles is the old measurement that's typically used, and it basically is a lumen, 1 lumen per square foot, and a lumen is the metric measurement of illumination. So if we were 1 foot away from a light source and we measured 1 foot candle, that is going to be 1 lumen per square foot. Now the metric measurement of that is a lux, and a lux is actually 10.76 of a foot candle. So, you know, 10's close enough, so a lux is about 10 foot candles. But it's measured further away. So it's at a meter away, and it's a square meter of measurement. Now, as we get further from a light, it's called the inverse square function. As we get further from a light, the light intensity goes down by the square of the distance. So you can see in our example here, if we're half meter away, we have 40 lumens per square meter. If we're a meter away, we only have 10 lumens per square meter. So that affects as we get further away from what we're trying to light, the amount of illumination we need goes up because it spreads as it goes out. So that's a factor when we're designing a light system. You know, one thing to look at in this is a study from New York State is where we're using lighting and how much. In this case, on dairy farms, we're using about 18% of our lighting, of our energy is lighting. So got light. Why are we lighting? We're lighting in some cases for security, although I think that's a false assumption, which I'll talk about a little later. If we have a work area where we need to see stuff, that's another area. And then productivity improvement. And this could be people. It could be the fact that we're lighting dairy cows so they produce more milk. It could be we're lighting to get longer days so we get longer plant growth. Those would be kind of areas of increased productivity. And then what are we lighting? Are we lighting a driveway? Are we lighting an animal exercise lot or a workbench? And that has to do with kind of the quality of light we need and the quantity we need, or the area we're trying to light. So that can affect what our choice would be. And then there's the amount of type. We have intensity, which is the sheer brightness or number of foot candles we need for a task. There's something called color recognition, which we're going to talk in a minute, which has to do with the quality of light. And then the color temperature, what side of the light spectrum is the light from. So we'll talk about all that. So a little terminology. They're lamps, not bulbs. I know, the incandescent light bulb, we've called it a bulb for years. But most other technologies are more than just a filament. We usually have a ballast or a driver that goes with them. So we technically they're called lamps. The fixture is all the things that go together to make up a illuminating device. So to be the ballast, the lamp, and often it's got a reflector or refractor with it, or diffuser. The light output is lumens, which is a measure of the power of light as perceived by the human eye. And just an example, a 60-watt incandescent is about 840, 900 lumens of output. The intensity, we can measure the intensity. We usually measure it in foot candles. And to give an example, an office desk is typically set up at 50 foot candles. In a dairy barn, we might only need 10 or 20 in the actual barn itself. Color rendering index is the ability of humans to perceive light under artificial, or perceive colors under artificial light compared to natural light, which would be sunlight. And then we have color temperature, and this has to do with the color, whether it's on the blue or the red side spectrum, and it's measured in degrees of Kelvin. So it's actually kind of mimicked off of a hot flame. And then we have lamp depreciation, which is a percentage of the reduction in the light output or illumination as the light ages. And most lights, as they get older, they put out less light. Light loss depreciation, well, that includes the lamp depreciation, but it also includes environmental factors like dirty diffusers that the light can't transmit through, or if you have a diffuser itself, even if it's clean, it reduces the amount of light that can escape because some of it's reflected off the surface. And then lamps are rated for life, and the average rated life that you'll see on a package is when 50% of the bulbs burn out or stop functioning properly. And some bulbs actually burn out, and there's some, we'll talk about HID lights, that actually just reduce in output until they hardly light at all. So first of all, a little more about color temperature. If we look at the light spectrum, we go from the very red to the blue, and basically if we're on a clear, low humidity day, we have a very blue sky. Well, that indicates a very high Kelvin measurement. So it would be 12,000 to 20,000 Kelvin. If we're looking at daylight, if we have a light that's actually advertised as daylight, that's usually in this middle of the spectrum here someplace. It's usually a very white light. So it would be in this 5,000 to 6,000, 6,500 Kelvin. Sometimes 7,000 you'll see. And then a lot of the older lights, they were, if you look at a package, they have cool white or warm white or soft white or whatever. they're toward the yellow or the red side of the spectrum. So they're down in this range, and there's actually sometimes very little difference between the numbers. But if you have two lights from those different spectrums, you can actually see one is a little bit whiter than the other, and one will have a little bit of a red tinge to it. And then lights themselves, because of the output or the light spectrums that they emit, will be in different ranges. So some outdoor lighting, high pressure sodium is kind of in the 2100 range. It's got a very orange type light, versus a mercury vapor, which tends to be in the blue or white side of the spectrum. Just for an example, a match or a flame is basically right down in this red. It's very cool. Typically, it's not a hot flame. So if we look at the light spectrum of different types of light outputs, here we have a warm light. It's going to be about 3,000 Kelvin, and we've got this spectrum of the light that it puts out. If we look at a warm light, which is just 100 degrees higher, you see the difference is basically in this red side of the spectrum. It has a little less red, and as we move up, again, we have a little less red, and then a little more of the yellow, and possibly a little more of the blue. And that goes on as we go up in the different ranges here. As we get up toward 7,000, now you see that the red side is down, and there's much more green and blue, and a little more of the purple coming into the light spectrum to be more of a more distributed light spectrum. If we look at the different types of lights, here's an incandescent. The wavelength it puts out, so it's more in the 7,000 nanometers than the 4,000. So this is in nanometers. This is actually in wavelength. If we look at a fluorescent, this is a warm white fluorescent. It's got more of the yellow. If we look at a cool white, it's got more of the blue, or it has more blue added to it, which gives it more of a white light overall. If we look at the mercury vapor, which is outdoor, it has a bit of, even though there's spikes in here, it's got some blue, purple, and violet in there. Versus if we look at a high pressure sodium, it's all the blue and red. It has hardly any in the, hardly any in the blue side of the spectrum. And if we look at a metal halide, which actually is a very high color rendering index, it has a very even output. So let's talk a little bit about color rendering index. This is the ability of humans to perceive light under artificial compared to sunlight. And the scale is 0 to 100, so it's basically percentage scale. So they've gone through and looked at it. You need 80% for color matching. So if you get 80% or higher, you're going to have a very good light. But different lighting technologies are kind of, because of the way they're built, are in different ranges. So a typical mercury vapor is about 15 versus high pressure sodium is about 22. Now they do have some that are in a better range, but they're typically on the low side. And then when we get into the metal halide and fluorescence, they're all quite a bit higher. They're on the high side of the spectrum. And I've got an example here. We'll just try to put this in perspective of what it looks like. So here's a picture. The top here is about a 50-60 color rendering index. Here in the middle we have a 70-80, and then we have 80 and better on the bottom here. So you can kind of see that the things here blend together in temperature a little bit. The brown isn't, it's kind of blued out. It also matters what kind of light these are, but it's kind of blued out. Here it's much more of a natural skin tone on the bottom here versus in the center and the top. And I think this next picture will really highlight it. This is M&Ms taken with a high-pressure sodium light versus more of a natural light. So in the natural light, we can see there's different colors. If we look at under the high-pressure sodium, things are yellowed or grayed together. I can't tell the difference between an orange and a yellow. This one's actually orange. This one's yellow. Well, it's just a slight perception of color. And you know, this one looks brown, even though it's green. And there's a blue one in here. I think, yeah, that's a blue one. It looks black. So it looks the same as the black one that's next to it. So you get these colors that kind of mesh together, so you can't really tell the difference. So the point is here, if I'm trying to do a detailed task, I need a light that puts out a high color rendering index. So bring it to agriculture. If I'm in a dairy barn and I'm trying to do health checks, and I need to know the color of mucus or discharge or something like that, I need to have a pretty high color rendering index. Otherwise, I may not be able to tell the difference between red and clear, just because of the quality of the light. Light depreciation. As lights age, they reduce their output. So some of the best here are a tungsten halogen light. LEDs aren't on here, but they're supposed to be very good. Some of the worst are a standard metal haloid, which has actually been obsoleted. But most of our lights are a good light. You want, for instance, a T8 and T5, they're about 10%. But when we do light modeling, we usually account for this, and we start out with a higher light level to begin with. And then the dirt depreciation, as I call it. If we've got a diffuser and we're not cleaning them, or we have an open fixture in the bulbs, depending on how often that's cleaned, we're going to depreciate that. So, you know, if we only get to about once every 3 years, you're going to have to start out with a lot more light to make sure that you're at the level you need on a long term. So some of the things that requirements, if we're designing or trying to figure out what kind of light we need in the level, is the level of light. So we need to know what task, as mentioned earlier. Some lights take time to warm up. So the question is, do we need instant on or not? So if we have something where we're walking in, grabbing something and walking out, we want instant on because we don't have the 3 to 5 minutes for maybe a high intensity discharge light to come on. Some lamps don't like to start in cold weather. Fluorescence is an example. A typical T8 or T12 lamp, under 50 degrees, they don't work very well. Luckily, the new ones, the T8s and T5s, are much better at that. So that's something to consider. You know, what temperature are we going to be using that? If we're looking at putting lights in a cold storage facility, for example, we need a light that will give us the proper level of light in that cold environment. The size and area to be lit. You know, if we're trying to light say a writing rink versus a workbench, we need 2 different types of lights to do that economically. The mounting height versus the work plane. The higher we get that light, the more it spreads out. We need to know the height of the work plane. So, you know, a typical desk is 2.5 feet above the floor. So that would be our work plane. If we're trying to do long day lighting for dairy cows, we need that work plane is now when they're laying down. So it might be only 1.5 feet above the ground. So we need to know where the work's being done because that's where we have to target our light level for. I've already talked about color rendering index. We may have a desire to have a certain type of color for mood or whatever. And the duration of lighting. If if we're lighting all night, we might want to get a very efficient light versus if we've got something we're only lighting for a few minutes at a time. Although some of that's changing because of new technology. So, old technology versus new. Incandescent bulbs, over 100 years old. It's old technology. It's been tweaked a little bit. The halogen is actually a type of incandescent light. But that's the old technology. And they're going to be replaced by compact fluorescents, T8s, T5s, and long term they're going to be replaced by LEDs. So one of the things that's going to force some of that is in 2007, the Energy Security Act increased the efficiency level that a light bulb or a light emitting device had to adhere to. And in doing this, basically it's in the 40 watt to 100 watt light bulb, incandescent light bulb area. And basically it raised that standard by 27%. So this basically negates being able to use a standard incandescent bulb. Congress has since rescinded some of this, but I suspect most companies have said, no, we've already changed our manufacturing and we're moving on. But essentially what that's doing is that we're gonna have to go to a higher efficiency bulb, which is good because there's lots of good choices and there's more coming down the pike. Now this doesn't affect specialty bulbs, so we're going to go over what you could replace that incandescent bulb with. There's no reason to hoard them, as I've heard some people doing. One of the benefits, why are we doing this? 18% of the electricity used in the U.S. is for lighting. So if we can up that increase, it's a huge savings. The average household, because of this, will save about 1,300 kilowatt hours a year, or about $160. And that's going to reflect in a U.S. benefit of billions of kilowatt hours of savings and many tons of CO2 emissions reduction. That standard also increases efficiencies again in 2020 to 45 lumens per watt. So we've got some time, and then it's going to jump again. So the replacements are a halogen type light, which is a type of incandescent. They just meet the standard. They're 27% more efficient. Compact fluorescent lights, which have been around for more than 10 years now. T8s and T5 lights, which are about 83% more efficient. And the newest thing in the market, they've been around for a while, but now the cost is coming down, is LED lights. And they're anywhere from 75 to 90% more efficient, but much longer life. At 130,000 hours, you're basically buying a light bulb for life almost, because it's going to last. So halogen, that's the first type we can do. As I said, they're about 27% more efficient. They have a little longer lifespan depending on the quality you get. Most of general purpose are about 1,000 to 2,000 hours versus about 750 to 1,000 hours for a typical general purpose light bulb. Low light loss appreciation, which is good. They're dimmable. One of the disadvantages is they have high surface temperatures. They will be phased out in 2020, so they are a temporary fix at this point. And they contain no mercury, so that is an advantage if people won't recycle them. The next thing would be a compact fluorescent. These have been around for, better part of 10 years, and during that 10 years they have increased in efficiency and variety that are available significantly. They're 75% more efficient, so it's a 4-to-1 basically. If you're looking at a 65 or 60 kilowatt incandescent, a 14 or 13 watt CFL would give you the same amount of light. They cover a wide range of temperature or of wattages and the equivalent wattages. So there's some that basically, if you've got a very high, like 150 watt incandescent light, there's ones that'll screw right into that socket and give you the light. They have high color rendering index, so that's good. Lasts long hours, so an incandescent is about 750 to 1,000. These are 6 to 12,000. They, I didn't put it on here, but they are affected. Almost all lights are affected by switching. So frequent switching will shorten their life, and compact fluorescents are no exception. So that is a disadvantage. So these are the rated life, and these are under a test condition, which is, I think it's 3 hours on, an hour off or something. I forget, but it's frequent switching to try to look at that. Starting temperatures, most go down to 20 degrees below zero right now, but some of the earlier models were 32 or 0 degrees. You have to look at the package to see what they're rated for. Most have a built-in ballast, but there's some that the bulb is actually separate from the ballast, so that does have some advantages. But most of them will save about 500 pounds of coal over the life of the bulb. And later on, I'm going to do some economic evaluation to show you what the advantages of all these technologies are. If we're going to use them in an agricultural situation, especially if it's dusty and moist, it's recommended they be in sealed fixtures. Now, these bulbs, the ballast is not made for heat. So in some cases, you'll need to look to find bulbs that are rated for an enclosed fixture. They're going to have a ballast that's made to run at a higher temperature. They should probably be protected. Actually, this type of light, which has enclosure, is what's required for barns. It has to be a sealed fixture from moisture. That's where you'd have animals. And the other advantage of doing that is these contain mercury, so we don't want to, even though it's a small amount, we don't want to get it into the environment if we can help it. A couple of years before that last Energy Act, there was the Energy Act of 2005, and it basically phased out electromagnetic ballasts for T8, T12 fluorescent lights. So that's already happened. The manufacturers came in and they supplied electronic ballasts to fill the gap. Basically, this was to increase efficiency. Electronic ballast is about 40% more efficient. The other option, and actually the better option, is to convert these to T8 fluorescents, and we'll talk about why and how you can do that. That increases the efficiency about 25%. The other thing you can do is if the fixture itself isn't in good condition or the wrong type, you can just replace it. And then you have choice of T5, induction, or maybe an LED to replace it with. So old versus new, the T12, which is actually a reasonably efficient bulb, considering incandescent, but it's older technology. If the lamps have shorter life and under 50 degrees, a standard bulb doesn't work very well. The light output is very low. So, as I just mentioned in the previous slide, these are the what we can replace it with, and we're going to go into this in a little more detail. So, a T8, they've been around for about 20 years or so. And the way these bulbs are named, these are 1/8 of an inch, so a T12 is 1.5 inches in diameter, a T8 is 1 inch in diameter, and T5 is 5/8 of an inch in diameter. So they're about 20-25% more efficient with the lumens per watt. But they're about the same. So a T12 and a T8, they're about the same output per lamp. So it's almost a direct replacement. The other advantage is we get longer life. So a typical T12 is about 1,000 hours, maybe 1,500 hours. The T8s are 20,000 to 30,000 hours. So you get more life for the money. The ballasts are more efficient. Starting temperature for the standard light's down to 0 degrees. So in many cases, I can use a standard light bulb in an agricultural situation. I don't need the high output version. And we'll talk about those in a minute. And there's no flickering. Because of the electronic ballast, there's no flickering. And sometimes we'll even light a little below 0. I've got them in my garage, and I know sometimes it gets cold. The T5 is about the same or 5% more efficient than the T8, but that's at the rating temperature. And I'm going to show you they're rated at 2 different temperatures. So it's kind of if you just look at it's 5% more efficient, that's kind of a false premise because you need to know what temperature it's going to operate at. These are mainly made for office buildings. That's their design. They're rated at 95 degrees. It came out of Europe. It's a metric length, so they don't fit, or they're not a standard 4 foot. Is the closest is 45 inches. They are about the same as a T12, so that's good. Down to 0 degrees. There's a high output version that's down to 20 degrees, and they come in a bunch of different lengths. These are not as readily available in retail stores, and the lamps themselves cost more. So I'm not necessarily a fan of them just because of that, and you're going to see a little more in the next slide why. T5s are rated at 95 degrees. T8s are rated at 77 degrees. Well, when we look at the lamp curve, higher temperature than that or lower temperature, the output falls. Well, if I look at, our average temperature in Wisconsin is 50 degrees or 47 degrees on a year-round basis, so I'm down here. If I look at that, a T8 is going to put out 72% of full output versus a T5 is only 42% of full output. So at those temperatures, the T8's a better selection. Now, typically, it's required that these be an enclosed fixture, which is going to hold the heat in. If it holds the heat in, it's going to move this up, so maybe they're about the same, even in a cold situation, if I've got them in an enclosed fixture. The same thing is true of a high output version versus a standard version. So the standard version is rated at 77 degrees. The high output version is rated at 59. So if I'm looking at these for a, say, freestall barn, and my lighting is basically, the majority of it's going to be in the wintertime, the high output version may be good because it's going to have higher output here at the colder temperatures. So it's all kind of the application it's going to be used for is which one's best. Retrofits. One of the advantages of a T8 and a T12 is they use the same sockets and they're the same length. So even if they're a single pin, the bi-pin is the most popular, and actually in some cases a 8-foot fixture will be actually 2 4-foot bulbs end to end is the way the manufacturers have been doing that. But they use, so if I've got a fixture that's in good condition and the correct type for the application, I can change the ballast and bulbs, and it's going to cost me about $30 to $50 for parts depending on the quality I get. I can convert those and gain 20-25% more efficiency. So that's an advantage. So, if I have to replace the ballast, or maybe even if I have to replace the bulbs in a T12, I might want to consider just go ahead and replacing and converting it to a T8 because, one, the lamps last longer, and I'm going to gain in that efficiency. So my maintenance cost is going to go down because I don't have to replace the bulbs so often. The electrical code in agricultural buildings requires that I have a fixture that is sealed and rated for damp environments. A dairy barn is considered a wet, damp, and corrosive environment because of the manure produces ammonia gas. So that's what's required. They also require that the switching devices be the same. A shop light is not acceptable for a barn that houses animals or is in dusty environment, even if it's dusty and dry. It would be acceptable for a farm shop where you have equipment, but no facilities. Many times, at least here in Wisconsin, we have rewiring programs for dairy barns or animal housing to offset the cost of upgrading the wiring in the barns, and part of that is replacing fixtures. So you might have people check with their local utility rep to see what programs might be available. The other policy change that came with that 2005 bill was to outlaw or basically discontinue the manufacture and import of mercury vapor lamps and ballasts. So after, well, I guess it's a ballast, maybe not the lamp. So there's no sales basically for 4 years now. So if you've got one of these, we need to change. The other one was a probe start metal halide, and when we looked at lamp depreciation, that was the worst one. So that's also been discontinued. The advantage of that one is there's a pulse start version that's available that's actually 25% more efficient. So that's the way to move on that one. So we'll talk about, so the mercury vapor, that's the old technology, and we can move to one of these other technologies to replace it. So mercury vapor is about 35 lumens per watt. Incandescent about 10 to 15, just for example. High pressure sodium is 2.5 times more efficient. So that's an orange or yellow type light. They tend to have low color rendering index, as I showed in that photo earlier. But it's similar to mercury vapor. It's just on the orange side of the spectrum versus the blue side of the spectrum. And the next would be to replace it with a pulse start metal halide light. Now these are twice as efficient, but the thing that people love about these is their very good color rendering index. Most of them are 70, some are 80%, so you can almost do color matching with them. But they are high lamp depreciation versus, say, a high pressure sodium light. The other consideration with what we call high intensity discharge light, which would be the mercury vapor, the high pressure sodium, or the metal halide, is that they require a ballast, and that ballast requires energy. So the most popular yard light is a 175 watt mercury vapor. It doesn't just use 175 watts, it actually uses 213 because it requires energy to run that ballast. So there's a little additional power there to operate those. So here's my test question of the day. How much does it, let me just get, no, I don't have my tests pulling. Let me just pull up something here. Let's see if I can pull this out. Well, there's a poll. If you go above the participant list, you're going to see something with an A in front of it. If you pull that, you can pick an answer, or we'll try it anyway and see if it works. How much does a yard light, 175 watt yard light, cost to operate a year? And this is one of my pet peeves with these, is that they, I think people don't understand how much energy that these things require. So I don't know if anybody found that, or maybe I've got to pull it out here. I haven't used this a lot, so I'm Still learning it myself. Wait, we only have one person that answered so far. Wait. Well, we'll go on because I'll tell you the answer here. Basically, the way we do it, we're going to run 12 hours a day. So we've got 4,380 hours. We take that 213 watts. We get 12 cents a kilowatt hour. We've got a little conversion factor to go from kilowatts or from watts to kilowatts. It's $112 a year to run that. And what surprises me is the number of lights that some people have scattered around their farm. And they often think they're security lights, but my pet peeve is if nobody's watching the hen house, all you did was light the way for the fox. The other thing we can do to use light more efficiently is to get it where we want it. So a common yard light has this refractor, and about 30% of the light goes up with these. So it lights the trees, it lights the side of the barn, anywhere but where we would really like the light. Well, we can buy these kits with a full cutoff reflector. So this is the part that would be added to the lamp. It just the diffuser snaps off and he snaps on a NEMA type light head. And there's a couple different manufacturers out there that have them, and you can buy these as a kit. They have a kit that you can buy that come with these. So when we go to replace that mercury vapor light, let's put a full cutoff reflector. Now people say, well, it doesn't supply as much light. Well, here's a test that somebody did. Looking at light on the ground and the distance from the light source. So this bottom line is just with an unshielded, and the top line is with a shielded. So we actually get more light to the area that we're really intending to light up, not the side of the barn and stuff. Now, sometimes you get some reflection from the side of the barn. It may perceive that we have more light, but we actually don't. So typically it's about 47% more light to the ground. Now if I take that mercury vapor light, the output's about 6,800 lumens. Well, 30% goes up, I only have about 4,760 lumens that would actually make it to the ground. Well, I could replace that with a 70-watt high-pressure sodium with a shield, and I would have more light on the ground and cut my cost in half. So that's just an example. Now, most of the time these come with the kit that I know of that comes with that full cutoff reflector is 100-watt high-pressure sodium. So you're going to have almost twice the amount of light on the ground after you put that up, although it's going to be more orange than it was blue. So that's just an example of how we can reduce our lighting costs. Another way is to control the light. Does the light need to be on all night? You already heard my little story about the fox lighting the way to the hen house for the fox. So, my point is, what are we lighting for? If there's not a purpose, we should turn it off. So we can do that with a time clock or a timer. That's one way to do. We can do it with a photocell or motion sensor. These don't work with HID lights, which are wide area lights, but they do work with like a halogen type light. The better option probably for a yard light type is replace the photocell. So they have a couple different types. They're called half-night photo sensors or photosensor with timer. And these can be either programmed for the time, so they can be set so they go off at 10 o'clock at night and back on at 4 in the morning, or the one that's a half night, it basically is on the first half of the night and off the second half, and it measures the night length and adjusts it accordingly. So I've given some manufacturers here with that have those devices. They're about 30 or 50 bucks, and they will pay for themselves. If you cut half the light, if you can see on 175 watt mercury vapor, they'll pay for themselves in a year. And it reduces light pollution as well to your neighbors. The other type of light that's not used very much, it's been around for a while, is called induction light. It is a type of fluorescent. but it lasts 100,000 hours. Now, why does it last that long is the typical fluorescent light degrades because it has electrons or electrodes inside the bulb, and as time goes on, they erode and until the fact that they can't get electrical discharge to light the light or provide a plasma ray across the light. These use a magnetic coupler on it to move those electrons around the field. So there's nothing inside this glass dome but the gases that I'm trying to see that will illuminate. They have high color rendering index. They come in a range of colors. They have high maintenance or low light loss depreciation. They operate over a wide range of temperatures, and they're fairly efficient. Not quite as efficient as a high pressure sodium, but they last quite a bit longer. A little higher capital cost, but you're paying for that life. You know, a lot of times what we need to do is we need to look at the operating costs and not just the upfront costs. They come in a range of types, you know, for you know, road lighting, to the side of a house, to something we'd use in a freestall barn. The other technology that I think is really exciting, and I think in 10 years this will be the main type of light that everybody's going to use, is LEDs. LEDs, or light-emitting diodes, and that's a picture of just one up in the top here, have been around for many, many years. They're used in electronics for indicator lights. They can be switched on. They have high switching frequencies in the millions of switchings at a time. So they're very efficient. And what the manufacturers are doing is taking a bunch of these little LEDs and putting them in to make a light. They'll last 25 to 100,000. Actually, I've just got one recently that advertised 130,000 hours. So that's like 20 years. High efficiency. They're getting better. Oh, and I guess I didn't mention it. We look at efficiency. It's lumens per watt, or the light output per unit of energy input. That's how we do efficiency. They are not sensitive to cold. They are sensitive to heat. So they actually have put more light output in cold weather and a little less in warm weather. So they're heat sensitive, not cold sensitive. Very good lamp depreciation. They have something called a driver instead of a ballast. It's a little bit different, but similar. They're very directional light, which can be a disadvantage depending on what the use is, but manufacturers are finding ways to sometimes use that to their advantage. I already mentioned switching doesn't shorten life. They don't contain mercury, but they do contain some other things, lead, chromium, arsenic, but they are recyclable. They have a aluminum heat sink in it that's very valuable to be recycled. So one of the manufacturers I talked to recently said they're willing to buy them back because they're 95% recyclable. So that's a good thing. So here's a little on the temperature. This red line's kind of, that's about 100 degrees, so that's kind of where we probably use these lights. And you can see if we rate them at 77 degrees, they come in a range of different colors. White is not a native, what they call a native light. The companies have figured out how to make white out of other colors, but it actually has almost 120% more light, 115% more light at minus 20 than it will at 77 degrees. So that can be an advantage. Now, one of the things that we need to do, or you've seen that we're going away from the incandescent bulb, is we need to start buying by lumens. So, and this is going to be tough for all of us because incandescent lights have been ingrained that we buy them by the watt. Well, if we have a 60-watt light bulb, that's about 900 lumens, and that's what we kind of need to learn to buy, is go by the lumens and not the watts. But I've listed the watts here so you can see that you know, a 60-watt light bulb would be about 43 in a halogen, about 13 is CFL, and 10 to 12 in an LED. So it just depends on the type of technology as to how many watts it will do. So we should start thinking about the lumens and not the watts. Now I'll put some dollar figures on this. So I'm going to example this 100 cal dairy barn approximately. We got 30 light bulbs, incandescent light bulbs, they're 100 watts apiece, 1,530 lumens, and they're 100 or 750 hour lamps. So what I want to do is I want to upgrade the lighting in this barn to have the same or increase the light level, but reduce my energy costs. So my technologies I'm going to look at here is a halogen, which is one replacing that 100 watt light bulb as of the 1st of last year. I got a CFL, which I can screw in, replacement. I've got an LED screw in, so that's this one. It looks yellow here, but when you turn them on, they turn white. Or I can do a linear fluorescent. I'm going to pick a T8 or a linear fluorescent LED. Now with these last two, I'm actually going to get considerably more light. So the important thing is I'm going to figure in what the cost of bulb replacement is on an annual basis, so that I get that maintenance cost in there. So I made a table up. So I got the watts, I got the life, the lumens per bulb, my cost of a bulb. Basically, I looked at Home Depot or whatever to get a cost, and then my annual cost. Now my annual cost includes maintenance costs. So, for instance, it's going to take me about 4 bulbs a year to cover the. I'm lighting 8 hours a day. 8 hours a day, 365 days a year. That's important. So to get that number of hours, I'm going to go through about 4 incandescent bulbs per year. So I've figured the cost of the bulb plus the electricity in all these. So this is what it's going to cost me to operate those. This is the savings compared to the incandescent. So my halogen is going to save me $280. My CFL is $822. My LED screw-ins, $767. The T8, which is going to give me, I think, 80% more light, is $840. My LED is $865. Well, the LED is $125 a bulb. What I did here is the lamp is going to be about $250 retail. I'm figuring in 20 years you're going to throw out the lamp. You're not going to, or you're going to replace the whole fixture. You're not going to just replace the lamps. The lamps are about $80 a piece. I figured we're just going to replace the whole thing in 20 years. So even with that high cost, that actually gives me the highest savings of all these, even though it's us. So we can't look at upfront cost necessarily. We need to look at the cost with maintenance cost and energy cost in here, so we can figure out what the best bang for the buck is. So this LED is actually a 2-bulb, 4-foot fixture, 23 watts. Disposal. Bulbs, everything contains mercury except an LED and an incandescent. And by state law in Wisconsin, I know Minnesota is this way, in many states, state law requires that these be recycled or disposed of as hazardous waste, and that's very expensive, so it's a no-brainer to do this. The good thing about recycling is they recycle most, they recover the mercury, they smelt the metals and reuse them, they reuse the glass. Contact your town or county recycling coordinator. If you're here in Wisconsin, you can go to this Recycle a Bulb website, and they'll tell you where you can drop off. This last one's for CFLs. But if you're in a different state, contact your recycling coordinators, and they can help you figure out where to take those. In some cases, they do charge a fee to get rid of these bulbs. But we need to keep the mercury out of the environment. It's already polluted our waters, significantly, so we need to recycle. It's a small price to pay. Here's a little chart. I'm not going to spend a whole lot of time on it, but if you want a bigger version of this, because I know in your handout you probably can't read it very well, but what I've done here is I try to list the bulbs by efficiency, the hours they'll use, the kind of color, light spectrum color, whether it's white or blue, the color rendering index, the temperature colors they're available in, the starting temperatures, whether they're instant on, and whether they contain mercury. If you want a larger version of that, send me an email and I'll give you send you a larger version of that. Going to go briefly into freestalls and going a little long here, but typically in a freestall we've got a couple of choices here. So one is a low bay fixture. The pulse dark metal halide is the choice that most people use. These need to have a cover on for a damp environment. And one of the things I want to point out here is different lights have different spreading or diffusers. So here we can see two different kinds. This one is going to give a more direct light, and we're going to have more of a light variation than a light like this where we have a bigger diffuser. And I've got an example of that hopefully we get to. The other option that many companies have been pushing now is these multiple bulb fluorescent lights. Basically, they have a higher color rendering index, although for a barn, it's not much of an advantage over a pulse dark metal halide, but they are more efficient, about 30% more efficient. So that's the big advantage. Now, if you've already got one of these in the barn, you can convert a T8 fluorescent to the LED bulbs with a little bit of rewiring. So that might be an advantage. But one of the disadvantages, these typically don't have a diffuser on it, so they don't spread the light as much, and we get more variation in light level. The option that I'm kind of excited about is LEDs. They make these for parking garages now and outdoor lighting, and some of these technologies we could use in a dairy barn. So the efficiencies of LEDs, they're evolving. The tube T8 type lamps I've got a sample of are 100 lumens per watt. There's some that are less. The 72 I think was this one that's pictured on the bottom. Rendering index is pretty good. They go up to I think 90%. They have a wide range of colors. The life is set up to 130,000 hours. Higher initial cost, but you know they're gonna. This is a technology that's evolving quickly. Every 6 months, there's new products on the market. If you're going in to put these in a barn, no matter what type you put in a freestall or a tie stall, what's going to hit that fixture? Try to get them so they're not going to get hit by machinery or animals. I like to hang them on hooks so they're easy to clean and maintain. Plug them in with a cord so that if you want to bring them down once a year, you should take them off and wash them to get the fly spots off and dirt. Have a spare one so if one goes out, you can just take it down and put a new one up and fix the broken one on a rainy day. So just some suggestions there. Light levels, typically for a barn, we're looking at 10 to 20 foot candles. The light level depends on the operation. You know, if I'm in office space, they design it for 50-foot candles. So if you got a lunchroom, you want 50. If you got someplace where you're doing inspection, like a wash sink, you might want 100. So it's going to vary depending on the type of operation. Light levels can be easily measured. There's a number of devices out there. You can buy them for about 80 to 150 bucks and more to measure that light level. If you want to do a one-time shot, you might check with your local cooperative extension agent. Sometimes they have them, or a lighting company. They may have one to come in and check your facility to see what the light level is. One thing to look at these is the light spectrum that they are rated at. So if you want to do it for a greenhouse, you probably want a little different device than if you're just doing it for general lighting. if you're trying to model, I recommend if you're putting lights up in a building, you should find somebody with a light modeling program to do this, especially if you're doing for a barn. So they have software packages that'll model the lights, and depending on the type of light you use will affect that. One of the things that's reflectance values. If you get somebody that's not familiar with ag buildings, we don't have ceilings, so there's no reflecting off the ceiling, so the reflectance value is 0. We have roll-up sidewalls, so there's no light going to be reflected there, so that should be 0. Tie stalls, the walls are usually pretty dark and decrepit, so that should be 0. And if anything, the floors might be 10%. So that's important, otherwise we're going to underestimate the amount of light. Manufacturers put out photometric light data, they're called IES files, that the light modeling program would use to estimate the lights. And those are available from manufacturers' websites. So you want to model the light you're going to buy, not just any old light. And there are some free programs out there. Lafoni is one that I use. Cooper Lighting has one. And there's others out there in the market. And a good lighting contractor will have his advantage. So what I wanted to do here briefly is to show you what, some choices when we use these. One is we can go with a high wattage light and use fewer lamps, or I can go with a lower wattage light and provide more lamps. And then I want to show you what the difference is between some different lights. So I'm picturing here is a typical light that's used in a freestyle barn. This is a 400 watt. And what I want to point out, it's going to be hard to see, but this is about 30 foot candles here at a hot spot right under a light, and it drifts out to about 9.4 halfway between these lights. This one's 11.6. So it degrades quite rapidly. So I've got a lot of variation in there. If I went to a 250 watt light instead of a 400 watt light, I have 40 lamps instead of 24 lamps, but my hot spot's 21 and the low spot's 13 over here where it's off the edge. Well, it's 13.8 kind of in between them and 16 between the lights. So I'm a lot more level is the amount of light level I had. It's a lot more even throughout. And then if I go to a different type of diffuser, so this is a light spreading diffuser, I can even drop it more. So now I've got 19 instead of like 21, and then there's about 15 between the lights. And this is a 400, so it's a high wattage light bulb. So I actually had 32 instead of 24. That's not always the case. I think this one's throwing a little more light upwards versus outwards. But what I'm getting at is you want to use the light that you're going to put in the barn. Oops, that one got repeated twice. I already did that. Quick calculations. If you're doing the calculation of energy, the total energy used in kilowatt hours is going to be the power. So if I get a 60 watt light bulb, it's going to be those watts times the hours it's used. And then I got to convert it into kilowatts, so I get kilowatt hours. Or convert the watts into kilowatts, so I get kilowatt hours. So a little example. Here's a 350 watt light. It's 8 hours a day, 365 days a year. Oops, I didn't change it here. I got 10 here and 12 down here, so we're going to use 12. So with the ballast, it's going to use 386 watts. So I got the 386 times 8 hours a day, 365 days a year. My conversion factor to get to kilowatts, and I get 1,112 kilowatt hours. I times that by my cost per kilowatt hour, and I end up with $133 a light per year to run that lamp. So just an example if you want to do some calculations. So what I want to leave you with is to change a light, change the world. Lighting is an inexpensive way to upgrade and save energy. And with the new technology, we're usually getting better quality, longer lasting light for less money. When we look at it on a yearly or operating hour basis. We need to avoid looking at just upfront costs. And here's some resources that you can use, and we're going to end it there. One thing I will say is that if you want to go out and use this program for a presentation on your own, you email me and I will send you the PowerPoint for your own use. So with that, we'll end it. And I will be sending out a post-evaluation here in an hour or so. We appreciate if you fill that out because that helps us provide our sponsors with information that lets us know that we've done our job and that this program made a difference, and that helps us get more dollars for doing more programming in the future. So I appreciate you attending, and I'll entertain any questions if anybody has a question. Geez, I did such a good job. Nobody has any questions? All right. Well, with that, we'll end today's meeting. If you think of something later, you can always email it to me, and I'd be glad to try to answer it for you. Thank you, and have a great holiday.